All right, welcome. Have you ever just stopped and wondered if there's a simple rule book for how everything in the universe works? From something as simple as an arrow flying through the air to planets orbiting the sun? Well, guess what? There is. And today we're going to unpack some of its most important rules. So let's start with this. What does a screaming, looping roller coaster really have in common with an apple just falling from a tree? The answer is pretty profound. It's that they are both governed by the exact same elegant set of physical laws. And by the end of this, you're going to see exactly how. First things first. Before we can understand the rules, we have to learn the language. And in physics, that language starts with how we describe things. The most basic distinction, it's between something called a scalar and something called a vector. Now, this distinction sounds simple, but trust me, it is a huge deal. A scalar is just a number, a quantity. How much of something? How hot is it? How long did it take? But a vector has that same quantity, we call that the magnitude, plus a direction. Where is it going? Which way is it pushing? That little extra piece of info changes everything. Think about it like this. Your mass is a scalar. It's just a number on a scale. It doesn't point anywhere. But the force of gravity that's pulling on that mass, that's a vector because it's pointing straight down. Your speed can be a scalar, like 60 miles per hour, but your velocity is a vector because it's 60 miles per hour north. The big takeaway here is, in physics, direction matters. A lot. Okay, so we've got the language down, now it's time to learn the grammar. And the grammar of how things move was basically written by one person, Sir Isaac Newton. These are the foundational rules for why things move or why they stay put. And the star of Newton's laws is the concept of force. You can just think of it as a simple push or a pull. But critically, it's a vector, right? The direction you push something is every bit as important as how hard you're pushing it. And here they are, his three famous laws. First up, inertia. Basically, things like to keep doing what they're already doing. If there's no overall force, things just coast. Second, acceleration. If you do apply a force, the object's motion changes. This is the big one. Force equals mass times acceleration, or F equals ma. And third, action-reaction. You can't push on something without it pushing back on you with the exact same force. So we've got forces making things move. Simple enough. But how do we actually measure the effect of that force over a certain distance? Well, that brings us to a concept you might think you know, but which has a very specific meaning in physics: work. Let me throw a little curveball at you. Let's say you push with all your might against a solid brick wall. You're sweating, your muscles are burning. After an hour, how much work have you actually done? In everyday language, you've done a ton of work. But in physics, the answer might just surprise you. The answer in physics terms? Zero. Zilch, nada. Because in physics, for work to actually be done, two things have to happen. You apply a force, and the object has to move some distance because of that force. If that wall doesn't budge, the displacement is zero, and so the work done on the wall is also zero. So let's check out a situation where work is actually getting done. Imagine somebody pulling this heavy crate across the floor. They're applying a force, right? And the crate is definitely moving. So even with friction fighting them, as long as that crate is sliding, a net amount of work is being done. And we can actually calculate this. And in this case, the net work done on that crate is 1,200 joules. Now, the number itself isn't the point. The real takeaway here is that work is a transfer of energy. And that idea right there brings us to our next huge concept: energy. You can honestly think of energy as the currency of the universe. It's what makes everything happen. And work? Well, work is just the act of transferring that currency from one account to another, or changing it from one form to another. Now, for what we're talking about today, we're going to focus on two main types. You've got kinetic energy, which is the energy of motion. And notice, its formula depends on mass and, really importantly, the square of its velocity. Then you have potential energy, which is basically stored energy an object has because of its position, like a roller coaster car waiting at the top of a giant hill. And this is where it all clicks together so beautifully. The work-energy principle tells us that when you do net work on an object, you are changing its kinetic energy. It's a direct trade. If you do positive work, you speed it up, you give it more kinetic energy. If you do negative work, like friction does, you slow it down and take kinetic energy away. It's that direct. So let's put this to the test with a real-world example. A car is driving down the road. If it suddenly doubles its speed, say from 30 miles per hour to 60, what do you think happens to the distance it needs to stop? You'd think it just doubles, right? Nope, not even close. It quadruples. And this is a direct result of that kinetic energy formula we just saw. Because the velocity part is squared, doubling your speed gives you 4 times the kinetic energy that your brakes now have to get rid of. 4 times. That's huge. We are not talking about a simple one-to-one increase here. This is an exponential relationship. It's an absolutely crucial insight for real-world safety because the energy you have to deal with goes up way, way faster than your speed does. And this has all been building up to the grand finale, the master rule that ties everything together, the law of conservation of energy. Let's go back to our roller coaster. Picture it. It's at the very, very top of the highest hill. It's barely moving, so it has almost no kinetic energy, but it is loaded with gravitational potential energy. Then it starts to drop, and as it falls, that stored potential energy gets cashed in, converted into the energy of motion, kinetic energy. It's trading its height for speed. But here's the magic part. Through this entire process, the total amount of energy in the system stays exactly the same. By the time it hits the bottom of the hill, whoosh, it's going as fast as it possibly can. Almost all of that potential energy has now been turned into kinetic energy. The form of the energy changed, but the total amount? That didn't change one bit. And that, right there, is the law in a nutshell. Energy cannot be created or destroyed, only changed from one form to another. It's like the ultimate accounting rule for the entire universe. The books always have to balance. Which leaves us with one final question to chew on. If that kinetic energy from the speeding car isn't destroyed when the brakes are applied, where does it all go? Think about it. What do your brakes and tires feel like after you have to slam on them? The energy didn't vanish. It just changed form once again.